Hello, sir.
Yeah, hello, ma'am.
I will start from my side, okay? Yeah, okay. So, good evening, Dr. Kamaraj, and good evening to the participants who are watching this live session. So, ladies and gentlemen, esteemed guests and dear friends, and good evening and a warm welcome to this exciting session on reversible logic design of arithmetic circuits. Today, we are diving into a topic that's not just about circuits or design. It's about shaping the future of computational efficiency and energy conscious innovation. Whether you are a seasoned expert in the field or simply curious about the fascinating intersection of technology and sustainability, this session has something special for you. And reversible logic is more than a concept, it's a revolution. It challenges the conventional boundaries of computing, offering new ways to reduce power dissipation while amplifying efficiency, a step closer to a sustainable digital world. As we embark on this intellectual journey, let's keep our minds open to ideas and our hearts open to inspiration and our curiosity alive to ask the questions that matter. So let's gear up for an inspiring and enlightening session again. So once again, welcome and let's make this a memorable experience together. So before we start Dr. A Kamaraj session, I would like to give some short introduction about him. So, ladies and gentlemen, esteemed guests and dear friends, it's an honor to introduce today's guest speaker, Dr. A. Kamaraj, an exceptional scholar and innovator in the field of electronics and communication engineering. So, Dr. Kamaraj, currently an associate professor at Mifkoslam Engineering College, Swahasi, brings over 17 years of academic and research experience to his work. And his educational journey reflects his passion for excellence, starting with a bachelor's in electronics and communication engineering and advancing with a master's in VLSA design and uh, culminating in a PhD in information and communication from Anna University. His doctoral research on reversible logic gates and circuits has opened new avenues in advanced arithmetic applications. So, and Dr. Kamaraj's achievements are nothing short of remarkable, with two patents granted and two more bending in cutting edge areas like intelligent helmets and advanced parallel process. He is a pioneer of innovation. His his portfolio boasts 54 publications in SCI and Scopus in text journals, garnering over 167 citations and an H index of 7. He has also co-authored instructional manuals and contributed to book chapters published by globally recognized publishers like Springer, providing invaluable resources to students and educators alike. So his contributions extend to quantum cellular automata and fault-tolerant computing and FPGA-based systems, solidifying his reputation as a thought leader in VLSI design. Beyond his impressive research his credentials, Dr. Kamaraj is an inspiring educator and mentor. He excels in equipping students with practical expertise in tools like Linux, ISE, and model sim languages such as Verilog and VHTL. So his passion for teaching subjects like linear integrated circuits, computer architecture, and low power VLSI design reflects his commitment to shaping the next generation of engineers. So please join me in welcoming Dr. A. Kamaraj as we look forward to an insightful session filled with knowledge and inspiration. And before we begin today's session, I would like to take a moment to introduce you to our company, Thames Tech Solutions, a pioneering Swiss venture. We are deeply committed to developing innovative engineering, management, and scientific tech solutions that are tailored to support your ecosystem with a forward-thinking approach. So what sets us apart is our dedication to affordability without compromising on quality. Our skilled and professional team is always ready to deliver exceptional business plans that cater to your unique needs. At 10 Solutions, we offer a wide range of services from digital marketing, web designing, and server management, on-field marketing, Android and iOS app development, telecommunications, AI tools, SC1, web analytics. So, and we also specialize in business operations and process automation across the multiple sectors, including industrial research, aerospace and defense, mechanical and automobile, electronics and energy, architecture and civil engineering, and medical applications, and more. So, no matter the industry, our solutions are designed to enhance efficiency and innovation and growth. In addition to our tech driven services, we are incredibly passionate about the education through our initiative. It's a mastering a platform. So this is a free platform is dedicated to unlocking the potential of young learners and providing them with the skills they need for a brighter future. And we warmly invite you to join us in this mission, and whether through the guest lectures or sharing your expertise, you can help uh, inspire and educate the next generation. It's a platform where knowledge sharing and leads to personal growth and fostering a community of enthusiastic learners and ready to take on tomorrow's challenges. So at the end, I would like to introduce to the motto of Dr. Kamaraj. The main motto: innovate, educate, and inspire, advancing technology for a smarter and sustainable future. So, finally, I would like to hand over the session to Dr. Kamaraj, and also a lot for joining us today. And over to you, sir.
Uh, Thank you, mastering up team of people for briefing about me and doing a social service in the technical field at a free of cost to the upcoming engineers. Okay, so without delay, I'll moving on to the today's presentation. So we'll be going to discuss about reversible logic design of arithmetic circuits in this session. So here we'll be going to discuss about two details. One is about how what is reversible logic and what are the how it can be designed, and the second thing is how this reversible logic design can be realized or validated. So these two are the major objective with respect to the entire presentation. So to in order to meet these presentation, the entire detail is divided into two major categories. One is about the completely reversible logic. What are the logic gates are there, and from that reversible logic gates, how various logical functions can be derived, and we are going to check the vulnerability of those reversible logic gates, and using these gates, we'll be going to build simple digital circuits. So all these things can be or has to be whatever the design which has been done by the designer. Ultimately it should be tested or validated. So in order to do that, in the software side, we'll be using a quantum cellular automata, which is a freely available tool, fast. So using that, we are going to we'll be going to see certain simulation and its results. So the very first thing is what is the meaning of a reversible logic? Maybe the term is new to some of you people. The term reversible gives a detail that the inputs and outputs can be interchanged. So which means that suppose if I'm giving certain inputs to a circuit, and it will be producing certain outputs. So if I am interchanging the details, the same output is given to the input side, we should or I should get back the inputs. So that is the meaning of a reversible logic. So for this reversible logic, why we need to go is it is mainly reducing the internally generated temperature coefficients. It is reducing that internally generated heat also. So that's the main purpose why we are going for this reversible logic. Actually, this reversible logic is very, it's not a new concept. Actually, this has been invented or introduced by Launder and Pennant during the year 1980s, 82, I think. So from that year, they'll be contributing, or they'll be keep on providing so many points, informations related to the reversible logic. One very key point is whenever there is a bit is lost in a digital circuit, whenever there is a single bit of loss is there, it is actually contributing to the KT log of 2 number of joules. So this much, this for a single bit. Suppose for this today's scenario, we can maybe the knowing that there are a lot of inputs are there, and we'll be having a lot of outputs are there. In between, there are so many bits are being compressed and compressed deliberately. So during this compression of or suppression of the information bits, there is always a possibility of heat generations. So this heat has to be reduced, or there is a possibility of reducing this heat, so that we can reduce ultimately the IC heat consumption. So uh, simply stating what is the meaning, or what is the concept of a reversible logic. Here you can see two diagrams. One is about conventional diagram, where we'll be applying two inputs A, B, and we'll be getting an one output and logic, A and logic, A and B. And here you can see that always we'll be having only one output and two inputs for any logic, conventional logic gates. If it is an AND gate, A and B is an input and only one output at the other end, Z. So which means that actually we are suppressing any one logical bit. Input side is two information, output is only single information, which means that we are compressing or losing one bit of information. So which causes the energy loss, as we stated, or as we seen KT log of 2. So here in the reversible logic, what we do is we'll be having the number of inputs and the number of outputs will be same. And additionally, here the red colored A and B actually indicating it is a garbage output. So only the useful output is A and B. In addition to that, we have a garbage output A and B. So A, B. So this A, B may be or can be used in the other circuitry or other part of the design wherever A or B is required. So it may be for the single AND gate, this going to be a garbage, but this garbage can be reutilized in the design effectively. So this, when you look into this reversible logic gates, three inputs are there and three outputs are there, so there is no information is lost. So we can avoid that KT log to heat dissipation. So that's a very basic idea behind this entire reversible logic gate. And how we are saying, or which gate or under what condition we are saying it is a reversible gate. So when we are able to make input and output is uniquely matched for the particular input, the output is also can be matched, or if I am putting reverse, vice versa, then this that particular gate is called as a reversible gate, or logically it is reversible. or the property, we can say it is having a reversibility, one to one, and in a single statement we can say that it is a one to one mapping between input and output. One to one mapping must be there for satisfying the reversibility condition. And with respect to the research point of view, there are a lot of works are there from the last 2 decades, maybe from the after 2011-12. There are a lot of people from the Indian scenario as well as international scenario. Many people are had done or contributed to the reversible logic domain. Initially people were very much interested in the combination logic design, maybe started from the inverter, adder circuitry, various types of adder circuitry, not only the full adder and RCA types of adders. Instead they were looking on to carry located or fast adders, such kind of adders also they were contributed. Later, maybe nearly 2018 onwards, people are slowly moved on to the sequential kind of things, sequential logics in the reversible logic domain. So in that sequential logic, as we already know that latches are being implemented first. Using those latches, edge triggered flip flops are introduced. So once flip flops are comfortably realized or designed, then we can move on to the counters and shift registers. So as far as the sequential circuit design is concerned, so only counters and shift registers are being done. In few people realized memory memories also, or memory arrays also, in order to contribute to the sequential logics. And very recently people are slowly moving on to the system level design, where arithmetic logic units and multipliers and dividers, very few are contributing to the dividers point of view. And few papers are really released or published in the AI domain also. So it is slowly evolving towards our AI domain also in this reversible logic. Okay, so now we'll be moving on to the basic reversible gates which is available in this domain. So the name Feynman actually derived from the person who invented this particular logic. Very simplest logic gate derived by Feynman, which has two inputs and two outputs PQ. Uh, so one among them, the one is a garbage. Normally, P is equal to A is a garbage, but still it can be used in some other purposes. Here, the useful logic mostly this is an XR logic. So not only XR, this can be or this entire Feynman gate can be configured as multiple different types of logic gates that will be see slowly in this rest of the presentation. So this is about the Feynman gate, two inputs and two outputs. Here there is a term quantum cost, which defines the characteristics or the performance quantifying parameter. So quantum cost one of the performance quantifying parameter for the reversible logic. Another parameter is how many number of garbage outputs we are actually having. So for the simplest gate and very low cost gate is Feynman gate with the quantum cost of with 1. And the next one is three input gate or 3 cross 3 gate. Here we should not use the term three input gate. Instead, normally we use 3 cross 3, 4 cross 3, 4 cross 4, or 5 cross 5. This is a terminology to be used whenever we are defining a gate. So the next one is a Fredkin gate. Again, the Fredkin is a person who invented this gate. Here, three inputs and three outputs. Here, when you look into the outputs Q and R, the complexity is a little higher compared to the previous Feynman. So Q is defined as A bar B XOR AC, and R output is A bar C XORed with AB. So why this complexity is introduced is, we can, when the complexity is there, we can able to derive so many number of functions from the given gate. So that is a purpose why we are always going towards increasing the complexity of the gate. In that way we can generate so many number of functions from the single gate. So that will be very much easier for the increasing uniformity of the design. So next one is Toffoli gate, which is very famously or very commonly used among the entire reversible logic design. So here also, this is also a 3 cross 3, and here normally two garbage output is there, and the main output is AB XORed with C. So this gate is a moderate one between the Fredkin and Feynman, so that this Toffoli can be used in a less complexity based designs, where we can easily introduce this Toffoli gate to derive whatever functions we are in need of. So that's why we did this Toffoli gate is very commonly used in many of the designs. So the first three, Feynman, Fredkin, and Toffoli, are the very basic gates. So using these gates, so many simulators are there, which is used to validate our design. So a few of the later researchers, they developed or they introduced their own gates. One among them is a Perez, whose output is Q is equal to A XOR B, and R is A and B XOR C. So Perez is also equally compatible with the Toffoli gate. With so many functions can be derived from the Perez gate also. And these were another two gates. One is new gate and HNG gate. So these are the again HNG is introduced by three different people. So that's why it is named as HNG. So here, when you look into the HNG gate, it is having a 4 cross 4 nature. Means that 4 inputs and 4 outputs. So here R and S, when you look into the R and S, R is A XOR B XOR C, which means that we can directly obtain some output of ABC from the R. So with the help of HNZ, we can easily design a full adder circuitry. So, so in order to understand the reversibility condition, so you just look into this. Here on the input side, 000 is there, and the output side 000 on the first row. So we cannot see any 000 on the other outputs. So this is called as a reversibility. So there is a one-to-one mapping between the inputs and outputs. Similarly, at the last row, 111 and output is 100. There is no 100 in the remaining part of the outputs. So these two are this is called as one-to-one mapping. So which means that whenever I am applying 100 in the input side, I should get or I'll be able to reproduce the inputs also. So these are about what various reversible logic gates which is at present available. So quickly summarizing, it is these are started from the Feynman gate, then Toffoli, Perez, Newgate, HNG are the various famously or very popularly used gates. Now we'll be moving on to the significant part of the presentation, which is deriving various logical function from this reversible gates. So here, this Feynman gate, we can generate NOT gate from the Feynman gate by introducing A input as A, and B input must be a constant one. So this is otherwise named as a constant input. And when we are giving this A as in one input, and B is fixed as a one, will be getting a output as inverted one, or the A is inverted output is available at the P Q output. So similarly, AND gate can be derived by derived from the Fredkin gate. Only thing is we need to put a zero in the C input of the Fredkin gate, so that we can able to generate or get the AND logic of AND logic using the Fredkin gate. Similarly, NAND gate can be derived by derived from the NG. NG here represents actually new gate. So new gate. So here, when you look into that, one is fixed at the C input. So you will be getting in NAND result at the PQ output. Similarly, OR gate can be constructed or derived by combining or cascading the two logic gates. One is new gate and Feynman gate. Fi here, here it is Fi represents the Feynman gate, two inputs and two outputs. So if I am combining these two, we'll be getting an OR logic. Similarly, NOR logic can be derived by slightly altering the functionality of new gate, where A and B input is given at the first and third position. Here we'll need to apply the constant input. So this constant input need not be one always. So for this, for our designs, till now we used only one as a constant input, but in various cases or some other cases we may be need of zero as a uh, constant input, so that we can derive the functions whatever we are need of. So this is a XOR gate. So for the XOR gate generation, we need not to modify any of the functions. Instead, Feynman gate by nature it is generating the XOR gate. So it is another point is it is not necessary that we have to generate XOR gate only from the Feynman gate. You can also generate from the Toffoli also, right? So but the thing is, we need to have a lesser cost ultimately. So the cost reduction is the main objective with respect to the design of any electronic circuits. For this case, reversible XOR gate with the with the Feynman, only quantum cost is one, so that's why we are using uh, Feynman gate in order to generate the XOR gate. And the XOR gate can be generated with the help of XOR with inverter. We already seen that the inverter can be derived from the Feynman gate by putting uh, one at the V input. So using that concept, we are now able to generate the XOR gate by cascading two Feynman gates. So this is how we can generate any number of logic gates from the reversible logic functions. Now we'll be moving on to the how this uh, uh, reversible logic gates can be validated with respect to two different functionalities. Already in the starting we discussed about the characteristic called reversibility. So that's a major uh, uh, um, characteristic which is expected for any reversible circuit or reversible gate. Similarly, there are two more characteristics expected for the reversible gate. One is universality and another one is fault tolerance. So we'll look into the meaning of an universality. So meaning of an universality is any logic gate which is any reversible logic gate which is capable of generating NAND and or function and a NOT function. These two are any of these three functions. If it is generating that particular gate, we can call it as universal function or universal gate. For the conventional logic, we say that NAND gate and NOR gate are the universal function or universal gates. So, if those gates can be derived from the reversible gate, that gate also we can call it as a reversible gate. So we'll look into how whether the proposed or whatever reversible gate we have seen, whether it is a reversible one or not, we'll see it. So when you look into the details, x1 Fredkin gate will first test the Fredkin gate, three inputs x0, x1, x2, and on the output side y0, y1, y2. These are all the outputs, and the inputs are here. Here now, according to the universality property, it has to generate AND logic, NOR logic, and inverter function, so that we can say that this particular logic gate is a universal gate. So when you look at the output of y1, just by fixing the x1 value as 0, x1 is 0, then we can get that, or we can see that this output is generating a uh, and logic for the 0 0, sorry, yeah. So this way, sorry, yeah. So this way, similarly, R operation can also be generated by fixing the x naught as x naught as 1, and if the x naught is input is 1, the x1 x2 alone kept as it is. So for this function y1 out, sorry, y naught output is generating an R function. Previously y naught function is generating and function. When you for the 1 1 case alone, 1, for the remaining function it is 0. So AND gate can be derived from here. Similarly, OR gate is derived by keeping x naught as 1. The similarly, NOT function of Fredkin gate is generated here. For the NOT gate, only one input x2 is alone there, and two constant inputs. Now we can when you see that x2 output, sorry, x2 inputs 1 0, we'll be getting a y naught as 0 1. So x2 and y naught combination producing a NOT gate function for the Fredkin gate. So we can now conclude that NOT gate, sorry, the Fredkin gate is an reversible logic gate with the universality characteristic. So similarly, when you look into the Toffoli gate, this is able to generate NAND gate by fixing the x2 as a 1 with the constant input, so that it is producing a NAND gate function at the y2 output. So when you look into the y2 output for the output, so it is producing a not NAND gate function. So Next, the third characteristic for any reversible logic is parity preservation. So this parity preservation mainly used in error detection or error correction in our conventional logical design or conventional circuitry. So for this case, reversible circuitry, fault tolerant meant that this reversible circuit is having a higher vulnerability with respect to the errors. It means that whenever this is a scenario to be satisfied, so all XR function of inputs must be equal to XR function of all outputs. So if this scenario is being satisfied, we can say that that particular logic gate is a fault tolerant. So for example, this is a Fredkin gate. For the Fredkin gate, when you do the XR function of all the inputs and outputs, it must be equal. So for the first case, A, B, C, 0 XR 0, 0 XR 0, so it is producing a 0. Similarly, PQR, when I am doing the XR function of all this is producing a 0. So similarly, when you look into the another case for the second set of inputs, the XR function is producing a 1. Here also it is producing a 1. So in the same way, we can test the fault tolerant for the entire cases. Similarly, for a Feynman 2 gate, the F2G actually represent Feynman 2 gate, means that it is a combination of two Feynman gates. Cascaded Feynman gate is otherwise named as a Feynman 2 gate. This is also having an fault tolerant. So till now we discussed about various reversible logic gates, and from that reversible logic gate we have seen that how we can derive various functionalities, and we have significantly seen the characteristics which is needed for the reversible logic gates. Now we are moving on to the how we are going to design some basic logic functions. So here this is a full adder subtractor. So this full adder bar subtractor can be constructed with the help of Feynman gate, Perez gate. So here we need a two Feynman gate and two Perez gate in order to get a sum carry function of full adder as well as difference borrow of a subtractor. So here whether it is to be acting as a full adder or a subtractor, which is based on the control signal available at this point. So based on this control signal, we can define this as a either full adder or subtractor. Here additional thing is only one constant input is used, and three different car bases are there. So for this case only with respect to the quantum cost, two Feynman gate quantum cost added with two Faraday's gate quantum cost. This is a quantum cost for this particular circuit, and three garbage outputs and one constant input. This is the performance parameter with respect to this full adder function. The same can be used for constructing higher order number of full adder functions. So next is a multiplexer. So multiplexer can be constructed with the help of Fredkin gates, but here we need a three Fredkin gates in order to design the reversible multiplexer. So here we'll be getting a final output y over here, and select inputs. Here we need to apply the select inputs at various places, S0 and S1. Here it is 4x1 multiplexer. So for the 4x1 we need two select lines. So these two select lines used to generate 4x1 multiplexer for the data lines. So here with respect to the cost function, three Fredkin gates, and garbage output is here one, two, three, four garbage outputs, and constant input. There is no constant input here. So comparatively, if the constant input is reduced or it is null, we can say that the performance factor is a little higher or little better for any design. So this is a reversible adder bar subtractor with for the 8 bit. So previously we constructed the single bit full adder bar subtractor. So when you cascade that full adder subtractors in multiple times, we can get any number of bits of reversible gate. So here only positive side is the when we are cascading it, the same number of garbage outputs and the same number of uh, quantum cost and same number of constant inputs are multiplied when we are augmenting, when we are expanding the design. But additionally, we can reduce the garbage outputs by incorporating this garbage outputs to some other places. So we can able to reduce the garbage outputs, but we cannot able to reduce the quantum cost and the constant input at the higher level systems. Only garbage outputs can be reduced at the system level. Only at the device level or a single unit design level, you can reduce the quantum cost and constant input, so that the higher level systems can be little effective or efficient. So this is an 8 cross 8 multiplex multiplier. So here we, as per we know that these are all AND gates has to be used, and in between we can introduce adders. So for this design, it can be realized with the 48 number of HNC gate and 8 number of Perez gates. So for this entire design part, it has a 103 number of garbage outputs, but still uh, the designer can able to reduce this garbage output by rerouting it. Okay, so till now we discussed about the uh, design part of the reversible logic. So now slowly we are moving on to the realization part or validation part of the reversible logic with the help of QCA, quantum cellular automata. So quantum cellular automata, before going into that, certain few basic information are need to be introduced to the listeners. So this QCA has a, a basic function or basic cell called as a QCA cell. This QCA cell, all QCA cells will be having four quantum dots. So these four quantum dots are actually having two electrons. So these two electrons normally it is present in the diagonal positions because of its Coulomb reaction or Coulomb repulsive force. So this position of electrons defines what is a logical value. So this is a example, quantum cell, single quantum cell where quantum dot is present, four numbers, and electrons will be there at any of the diagonal position, either this position or this position. Based on that, we can say that this will be of representing, or this is representing logical 0 or logical 1. Okay, so here this is when the dots or electrons are present at the diagonal position like this we can say it as a logical 0. Similarly, on the opposite case, we say it is a logical 1. And it is representing the polarity. P represents the polarity. It is represented the polarity with the -1. And for the logical one, it is +0. +1. Excuse me. And very significantly, for any QCSL, it has to be driven with clocks. There are four clock zones normally used for the QCA clocking: clock zone 0, 1, 2, 3, and all the clock zones are having 90-degree phase shift with respect to each other. So when the switching phase is here, the after 90-degree, the next clock zone is having a switching phase. Another 90 next clock zone is having similarly next. So every clock zone is having a 90-degree phase shift with respect to the previous one and the next one. So which actually and collaboratively saying 360-degree for the four clock zone. The reason why we need a four clock zone is the data has to be, ultimately the data has to be transmitted between the various cells. What we do is, in each cell is representing a equivalent of a transistor, commercial MOSFET transistor, logical 1 or 0. So this information has to be transferred or transmitted to the nearby cells. For that, it has to be driven by proper clock signal. So that proper clock signal can be given with the 90-degree phase shifted clock zones like this. So another major constructive method of any reversible logic in a QCA is a majority voter. So this majority voter is having an four five cells. Among them, any two cells having a same polarity or same logical function, that will be the final output. For example, if B and C is having a logical 1, output should be of 1. Otherwise, if B and C is having a 0, then output must be 0. So using this concept, we can generate or construct the final QCA cells. So here two types of wires are used for the design of QCR based reversible logic. One is normal binary wire, another one is inverter wire or inverter chain. So this we have seen in the previous sample. So this is actually representing a logical one. So if I keep on making a same cells, every cell is having this same logical value, since the electrons will not align to each other. So this electron will repel this one. So it will not, this electron will not reside at this place. Instead, it goes there. Same cases for this one. So because of this function, any signal which is being applied here, the same can be transmitted or transferred to every cells. Here inverted in the sense it is a 90-degree phase shifted. The normal cell is 90-degree phase shifted. So in this case, when you look into the nearby cells, it is always having an alternate function. If it is 0, this becomes 1. The next it is 0, 1, so and so on. So wherever inversion is needed, these kind of cells can be used to provide or to make an inversion. And two kinds of wire crossing is there. One is coplanar wire crossing, another one is multi-layer wire crossing. For the coplanar, we are uh, we are having uh, single layer is consisting of all the cells. So all the cells are residing in the same layer. So this is a schematical view of coplanar wire crossing, and this is a way in which normally represented, or it is being constructed. So when you look into this wire crossing, we have a two set of wires. One is normal wires, another one is inverted chain. So the same plane, we can have both the kind of wires. So it will actually reduce the area for the design. But the drawback is sometimes logical degradation may happen. So this is a QCA realization and the corresponding output 1 and 2. The same input is being followed in the output side. Second one is multi-layer crossing, where this multi-layer crossing is actually similar to the bridge concept. So underlying signal will be carrying one kind of signal, and the second floor or a bridged signal, the bridged line will be having carrying another signal. For the construction of a bridge, we use two more special cells called as via and a crossover. So like this, at least four vias has to be used. After that, crossover cells to be used, and then four more vias to bring into the normal cells. So this is how normally construction is being done, and we need additional layers. So the drawback is additional layer, but the positive side is it has a better logical output. No degradation happens. So this is what realized in a QCA tool, and the same output we can get it. And the various logical function, this is for the simple inverter. So this inverter can be designed with the help of, so you can see that 0 is being pushed on and it is converted into, sorry, 1 is being pushed on and we'll be getting an output as 0 here. So initially 0, output is 1. When we are pushing logical 1 over here, then we get logical 0 here. Similarly, half adder can be you constructed with the help of majority voter, and you get sum and carry here. And this realization, when you this via cells and crossover cells, indicating that this is a multi-layer concept or multi-layer realization. And similarly, this is a full ladder construction using a majority voter, and this majority voter full ladder logic gate over here, and this is a memory cell array, which is with the multiplexer 2 cross 1 mux over here, and the read write signal, and the row select and column select lines are being there. Here a single memory cell was there, so only one row select alone we used here. And using this single memory cell, we can now able to construct a 4 cross 4 memory array. This is a construction of a 4 cross 4. Here each, this is this single memory cell. Similarly, column wise and row wise multiple in single memory cells are there. So these memory cells can be either individually accessed or complete block wise accessed with the help of read line or row select lines or decoders. So this, with the help of decoders, either we can do the writing operation, reading operation of a single cell or multiple number of cells. So yeah. So with this, we can conclude this presentation for the reversible logic design of arithmetic circuits and its realization in the QCA tool. So this QCA tool is an fast tool. Anyone can download it from the internet at free of cost, and you can design it, export your design, and do the publications also. And thank you all. If you have any queries, you can always write to us for getting more clarifications.
Yeah, thank you, sir. Thank you so much for the wonderful presentation. And just wait, sir. Okay, sir, shall I ask some questions? Sir, shall I ask some questions? Hello?
One second, ma'am.
Yeah, okay.
Yeah, yes, ma'am.
Yeah, okay, sir. In my first question, how can reversible logic gates minimize power dissipation in high performance arithmetic circuits compared to traditional designs?
Uh, this is a very inherent property. Means that the logical function or the logical bit is not erased during the computation. So KT ln to heat dissipation is being ignored or reduced. So due to that, we can able to generate higher performance circuitry with less power reduction using the reversible logic.
Okay. So, what are the key challenges in implementing reversible logic in large scale arithmetic circuits for real world applications?
Actually, till now there is no fabrication methodologies available. So people are doing many researches towards implementing this in a larger scale. But still now, yeah, as well as in America, there are many kind of fab units are there, and they have implemented their own reversible logic based QCS cells. Or if you can just Google it with the term QCL labs or reversible logic lab. There are a lot of labs are being slowly emerging in India.
Okay. So, how does the integration of quantum computing principles enhance the functionality of a reversible arithmetic circuits?
With respect to the modern functionality, still it is facing lot of issues with respect to the reversible logic design implementation. It is facing lot of issues, mainly as said the fabrication side. And the second thing is we need to control in the electron level. So for that electron level, still many uh, tools are not available. CAD tools are not available. So the CAD designers are facing lot of issues with respect to the design of tools. Once the tools are evolved, we may be slowly able to produce a lot of commercial products using the QC designs. So we may be expecting, or we can expect maybe within a 5 to 8 years, commercial QCA based reversible logics will be available.
Okay. Okay, sir. My final question. What role do reversible logic circuits play in advancing energy efficient computing in IoT and wearable devices?
With respect to the wearable devices, there is no research or concept being evolved. But with respect to the perception, my perception is once the commercial QCA design is available, ultimately it will be automatically contributing to the any kind of field. It is not only going to be the wearable devices or wearable logics. Maybe for any computation at any points, this QCA based designs can be incorporated. So there is no limit of domains or fields.
Okay, thank you, sir. Thank you so much. So, thanks for the useful answers. The access is very useful. I hope the access and the participants can understand about that. So, finally, so ladies and gentlemen, esteemed guests and dear friends, as we come to the conclusion of this enlightening session, so it's my privilege to extend a heartfelt vote of thanks to our distinguished guest speaker, Dr. A. Kamaraj, for sharing his profound insights and expertise on reversible logics, design of arithmetic circuits. So, Dr. Kamaraj, your presentations not only deepened our understanding of this transformative field, but also inspired us to think critically about the future of sustainable and efficient computing. So, your ability to simplify the complex concepts while highlighting real world applications is truly remarkable and has left an indelible mark on all of us. So, on behalf of everyone here, I express our deepest gratitude for taking the time to guide us through this innovation domain. So our passion for education, research and mentorship and shines through motivating us to embrace challenges and contribute meaningfully to the field of technology. So thank you once again, Dr. Kamaraj, for your invaluable contributions today. So we look forward to the opportunity to learn from you again in the future. So let us all give a big round of applause to our appreciation. So thank you, sir. Thank you so much.
Thank you, ma'am. Thank you all.
Yes, sir. So just a minute, sir. Sir, can you able to see the virtual Momoto?
Yeah, yes, ma'am. Yeah.
Okay, great, sir. So, sir, on behalf of Mastering Up, we present this virtual memento as a tribute to our guest speaker, Dr. A. Kamaraj. So, your insightful contributions have enriched our knowledge and inspired us profoundly. So, this token of appreciation symbolizes our gratitude for your expertise and dedication. So, thank you for sharing your wisdom with us and shaping our understanding in profound ways. So, thank you, sir. Thank you so much.
Thank you, ma'am. Thank you. Thank you.
Thank you, sir. So, shall I leave the session now?
Yeah, yeah. Thank you.
Yeah, okay, great, sir. Thank you.